I'm Pat Dugas and welcome to Systems of Equations. We're going to focus on numeric and graphic methods of solutions in this screencast, and then the second part we'll focus on the analytic methods of substitution and elimination. Let's look at terminology involving systems of equations. A system of equations is a situation where we have two or more related equations with the same variables. And our goal is to find the solution or solutions, if they exist, to this system of equations. A special case of a system of equations involves finding the break-even point, which in a business or financial situation is where the system of income, which is on one line, is equal to the cost function, which is on another line. That's often a very important point in business. So some definitions. A system is consistent if it has one or more actual solutions to it. There are two types of consistent linear systems. One is an independent system that has only one solution, two lines meeting at one point. That's kind of the typical situation. We also have an atypical situation is when they're dependent, infinitely many solutions. This is when the two lines are actually the same line. And finally, we have a situation which is called inconsistent, and that's where the system has no solutions at all. It's where the two lines really do not meet, and typically that's because they're parallel to each other. Let's take a look at the different processes, the different methods for solving systems of equations, because they're quite important. And this is typical for all of mathematics. There are really three different major ways to solve things. First of all, we can solve this system graphically. We can make a graph of it, and we can look to see where the lines intersect. That's the solution. What we're going to focus on in the next screencast is the algebraic methods, analytically, using two predominant methods. One is substitution, the other one elimination, to algebraically find the solution. Finally, we're going to focus on the numeric solution in this screencast, and that is the process of making a table and looking to see where the values, the output values in the system of the two lines or more lines are the same. Where that occurs, that's a solution to the system. So let's look at a numeric solution, which involves making a table. So let's say we have a system of equations, x plus y equals 3 and negative 2x plus y equals negative 6. We want to solve it by making a table. Well, what we're going to do is we're going to make a table of x plus y equals 3, those values, and negative 2x plus y equals negative 6, those values. We're looking at x and y coordinates that make up those two lines. Okay, so x plus y equals 3 becomes y equals negative x plus 3 because we subtract an x from both sides. In the other equation in the system, we're going to add 2x to both sides. We're going to use the addition property of equality. And that's going to put it in a nice slope-intercept form, which makes it easier for finding coordinate points. Once we've done that, we can make a table. This is the first equation. y1 equals negative x plus 3. We're calling it y1 because it's the first equation in our system. And then we have y2 equals 2x minus 6. These are the two equations in our system. So we're going to find x and y points, coordinate points, for both. So we're just going to try different numbers. This is really why the numeric process tends to be a longer, more involved process, because it's kind of a little bit of luck and guess and check involved. So if we try x equals 1, the first function becomes y1 equals negative 1 plus 3. We're substituting a 1 in for x, so we get a 2. So the first point is 1 comma 2 with this line. Well, if we put the same value of x equals 1 into the second line, we get y2 equals 2 times 1, substituting a 1 for x, minus 6, which is negative 4. So the first line, we get the point 1 comma 2. The second line, we get the point 1 comma negative 4. These are not the same, so we've got to keep going. So then we look at x equals 2. So when we have placed in a 2 in for x, we get 1. Negative 2 plus 3 is equal to 1. In the second line, we get 2 times 2 minus 6, which is negative 2. So our 2 points here, 2 comma 1, 2 comma negative 2. They do appear to be getting a little bit closer to each other. Here they were 6 units of y apart. Now they're only 3 apart. So it kind of makes sense that we're getting closer to the solution. You want to try to look at those kind of things if you're having to do things numerically. Honestly, I think it's the least efficient of all the processes. That's kind of where we're starting with it. So x equals 3, put it into the first equation, we get 0. Negative 3 plus 3 is 0. X equals 3, put it into the second equation, we get 2 times 3 minus 6, which is also equal to 0. So our points are 3 comma 0 on the first line and 3 comma 0 on the second line. Bing, 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 we have a winner. That means the point 3 comma 0 is going to be the solution. Let's look at the graphical method of solving systems of equations. So we're going to look at the equations x minus 2y equals 0 and x plus y equals 6. And we're going to solve this system of equations to find the solution by graphing. You do not actually have to write each equation in slope-intercept form. That is often helpful, but these are in standard form. And you can graph them this way. You can find the x and y intercepts and go from there. But we'll go ahead and put them in slope-intercept form. So if we use the addition property of equality and add 2y to both sides, and then we use the division property of equality and divide both sides by 2, what we wind up with for the first equation in slope-intercept form is y equals 1/2 x. The second equation works out very simply just by using the subtraction property of equality and subtracting x from both sides. And so in slope-intercept form, that equation becomes y equals negative x plus 6. So let's go ahead and look at a graph of that. So if we graph y equals 1/2 x, then we wind up with this line because it does go through the origin and then has a slope of 1/2. So if for every 1 it goes up, it goes 2 to the right. So that's the first line is what that x minus 2y equals 0 or y equals 1/2 x looks like. Then when we graph negative x plus 6, it has a vertical intercept of 6 and a slope of negative 1. So for every 1 down it goes 1 to the right. So that's the second line. So the solution to this system is where they come together. Their intercept is at 4, 2. Now, graphically, we determine that simply by looking at the graph. So it's very important in this method to draw an accurate, well-proportioned graph. So when you do that, you can fairly accurately determine the intercept. So 1, 2, 3, 4, 1, 2. 4, 2 is the intersection and is the solution. So this screencast was about systems of equations, looking at the terms, and then being able to solve them using numeric and graphic methods.